All right, good afternoon again.
Morning or afternoon.
Yeah, whatever it is, it's a good one.
Morning, afternoon, yeah.
Afternoon.
I was in the middle of registering for more classes, but apparently there's been a lot of conflict between classes, especially with registering for CSE215.
Oh, really?
And yeah, I kind of wish there was more options and stuff like that, but I'll have to work something out.
What is 222 conflicting with?
Well, so there's one for Mondays and Wednesdays between 10 a.m. and 10 p.m.
Mm-hmm.
But there's a business class that starts right at 12 p.m. So and I don't think those will work well together since I need kind of, don't want to have like 10 minutes conflicting with my other class.
Okay, if that's your only option, we should talk about it, cause
Yeah,
10
yeah, we
minutes
can
is
talk
not
about
the
it
end of
in
the
office
world.
hours.
It's a 2-hour class. The last 10 minutes, other than maybe for long exams or something, we can probably talk about that and figure something out. If that ends up being your only option for physics and for 222.
Yeah, my other option was to take physics at the university if that's an option.
Mm-hmm. Okay, yeah, let's talk about that in email or office hours and see what the possibilities are. All right, we've only got 14 people here, but go ahead and send me an attendance ping anyway. Let's see who the 14 are. Awesomeness. And any questions before we start? So I'll try to get your homework graded before Friday, and get that back to you, and hopefully we'll be able to talk about it on Friday, um, and wrap up the section on counting. I wanted to just finish up briefly one thing we were talking about on Monday. We were looking at Fibonacci series, and we were also starting to talk a little bit about recursion. And I had shown you this piece of code which lets you do Fibonacci series in C, and this is a very sort of straightforward interpretation of what a Fibonacci series is, which is, a sequence of numbers where each number is the sum of the two numbers immediately before it in the sequence. And so, I'm using last and last two to mean the previous and the previous numbers, and I'm seating those at 1, and I just set this current number to the sum of the two previous numbers, and then I shift everything down one spot. And I generate Fibonacci's like that, and it will, run very efficiently. It doesn't take, any time at all to calculate the nth Fibonacci number from the n minus first and n minus second. You just add the two numbers together, right? And we're overflowing the 64 bits of a long integer, but this is running just fine. So there's another way that we can code this, and this will be something we'll do a lot more of in CSE222, but just as kind of a first intro to this maybe, here's a totally different approach to the Fibonacci function. So I'm going to make a loop that generates the first 1,000 Fibonacci numbers. And I'm just going to call my Fibonacci function. I'm going to pass it an integer n and get back an answer. And my entire function is this. It's just a few lines of code. And it comes directly from that recurrence relation that we used to describe the terms of the series, which was, if I want Fibonacci of 1, it's 1. If I want Fibonacci of 2, it's 1. So if I call this with a value of 1 or 2, this if statement will say, hey, just return a 1. For anything else, the Fibonacci value corresponding to n is the sum of the values at n minus 1 and n minus 2. And how do I get Fibonacci of n minus 1? I'm just going to call Fibonacci n minus 1. And how do I get Fibonacci n minus 2? I'm just going to call Fibonacci n minus 2. And this may look a little bit like we're cheating somehow, but this is 100% correct. And the way I know it's correct is because I know my Fibonacci function works for n equals 1 and n equals 2. How do I know that? Because of this if statement right here. Right? I know that if I call this with n equals 1 or 2, it's going to return a 1, and that's the correct thing it should return. That's my base case in my inductive proof that this function is correct. My inductive step says, suppose that this works for n minus 1 and n minus 2. Will this work for n? And this statement right here tells me the answer is yes. As long as fib works correctly for n minus 1 and n minus 2, this line will return the nth Fibonacci number, so this function will work for n. And so real simple, inductive demonstration that this function will return the nth Fibonacci number. And if I compile this and run it, sure enough, it will calculate Fibonacci numbers. So here's our familiar sequence, 1, 1, 2, 3, 5, 8, 13, 21. Each number is the sum of the two numbers before it. But look at the speed of this thing, right? This thing is really working. So it just found the 45th Fibonacci number. It's working on 46. And it's taking a really long time. And it will finish 46. I don't think it will get to 50 in any reasonable time. And my CPU is just slammed right now. Right? I'm spending 100% of my CPU running my fib function. So this is all, doing intense calculations right now. And if I had just done this, to calculate the 47th Fibonacci number, it takes one line of C code. And I just take the 46th and the 45th. We could do this with a pocket calculator. I could take these two values, add them together on paper, and I would get the 48th Fibonacci number faster than my program is. Right? I could add these and get the 49th. And so this is one example of where a recurrence relation may give you something that is technically a way to, calculate or present the nth element of a series, but it may not be efficient. And in this case, this is really inefficient. Sorry, say again?
I got a question.
Yeah.
I'm kind of curious about why would it take such a long time for a computer to calculate a really big number from a previous number. Is there some kind of what's the behind the scenes of what the computer is actually doing to calculate?
So
navigating the whole stack, right?
Yeah.
That's
So
why
this
it
is
takes so slow.
This is
Okay.
an interesting question. So suppose we want to calculate. We're writing a recurrence relation. So f of 1 equals 1, f of 2 equals 1, and f of n is f of n minus 1 plus f of n minus 2 when n's bigger than or equal to 2. Alright, so how do we find f of 3? It's just f of 2 plus f of 1, which is just 1 plus 1, which is 2. Not a big deal. Suppose I want to find f of 30. Well, I need to calculate f of 29 and f of 28. And to calculate f of 29, I need to calculate f of 28 and 27. And to calculate 28, I need 27 and 26. And to calculate 27, I need 26 and 25. And this needs 24 and 23. And if I start writing out exactly what this tree looks like, I'm going to find a huge number of calculations that need to be performed to find this thing. And the number of calculations I'm going to have to perform is increasing. And it's actually increasing by a Fibonacci series, which is kind of cool. And so if we just look at f of 5, and let me just write the numbers instead of the f of. To calculate 5, I need 4 and 3. This needs 3 and 2. This needs 2 and 1. This needs, this does not need a recursive call. This needs 2 and 1. So all of that has to happen to find f of 5. Now if I want f of 6, I've got to do f of 5 and f of 4. Well, this is going to involve all of this work, and this is going to involve all of this work. And the number of steps it takes to calculate the nth term is basically the sum of the number of steps it needs to calculate the n minus first and the n minus second term. And so this number, which is increasing, is also showing me how much work I have to do to get the next number. And it's just a ridiculous amount of work. So we'll use recursion a lot in 222. We'll work with a lot of cases where recursion is a totally reasonable and actually excellent choice for how to solve an algorithm. And we'll find ways to deal with this kind of situation to speed it up, and we'll be able to do a recursive Fibonacci function that'll run as quickly as our original straightforward version. So that's all stuff that'll be coming up. It's kind of a preview of coming attractions. All right. So I just wanted to finish that up, and I'm gonna give my CPU a break and kill this because I'm probably getting. I'm also getting these like temperature warnings where it's like throttling back the CPU because it's overheating. So good stuff. All right. So let's go on to the next unit of this course, which is graph theory. And so I've posted a new homework assignment. This does not come out of the text. It's just a sheet of problems I've made up, which will be due in a week. Let's see. It has to keep calling itself over, and when it finds the right number, it has to go all the way back up the stack. Yep, exactly. So yeah. And this will be a typical feeling when we think about recursive code, is sort of going down a rabbit hole deeper and deeper and deeper, and eventually hitting a base case that pops us back up. And that's the same kind of thing that happens in inductive proof sometimes, right? If you want to find, the sum of the first 100 integers, well, you have to know what the sum of the first 99 is, and then add, 100 to that. And so you work your way down until you get to a base case. What's the sum of the first integer? Well, that's just 1. And then you can use that to find sum of the first 2, first 3, and pop back up. The sun is out. I'm not sure what this thing is in the sky. It's glorious.
It's so windy out today.
Is it?
Real windy over here in Camas.
Oh, I'm pretty close to you, so yeah, the trees are doing their thing. All right, so we're going to talk about graph theory. This is another branch of computer science. It's going to use some new concepts, and it's going to involve thinking about information in different ways to represent these things called graphs. So let me give you the hand-wavy version of graphs first, and then we'll start making it a little more precise. But what is a graph? Bunch of dots, bunch of lines connecting them together.
Was there a question like this on today's homework, where you're trying to calculate how many lines you can make based on how many dots you're given?
No, that was a different kind of question. That's still a permutation combination question that had to do with particular dots on a page and connecting them with lines and so on. But we can think of this as maybe an example of that kind of setup. But what we're going to do with this is going to be fairly different. There's a lot of crossover between all these topics. It's always cool to sort of see how they relate. But the graphs we're going to talk about here, this is sort of the picture we might have in our mind when we think about a graph. But one thing to keep in mind with graphs is where I draw the dots is really irrelevant for what we're going to be doing in this unit. the fact that, you know, there's a dot here and a dot here and a line connecting them is extremely relevant. The fact that, you know, I drew a curved line there and a straight line here makes no difference. And if I had drawn this dot over here instead, makes no difference. It's the same graph. So abstractly, we're kind of thinking of a graph as just a bunch of points connected with lines. And some of the things to keep in mind when you're thinking about graphs, typical example that comes to mind for us is something like a computer network. So each of these could be a computer, and each of these could be, you know, something connecting two computers together. Could be a piece of wire, it could be, you know, an active Wi-Fi connection, but we could think of this as a picture of a computer network. And if you think old school, where you actually run, you know, Cat5 cable from machine to machine, so these things are physically connected, these would represent, you know, things that have cables between them. And we can start to analyze a system by looking at a graph and say, for example, you know, from here, is there any way to get information to here? And it turns out there is. We could send information from here to this machine and have that one relay it over to that machine. But it's going to take a little bit of time. We're going to have to go 1 hop, 2 hops to do that, as opposed to if we had a wire directly from here to here. And this machine over here, we can get to this machine by going 1, 2, 3, 4 hops. So yeah, it's like a map. And yeah, I've got Cat5 all over my place right now, but I figured I was just old school. I like Cat5 because it's fast, you know, and it doesn't flake out, and Wi-Fi, I don't know. Wi-Fi is so convenient, but like going to my external drive, I just use a hard line because I can get like really good bandwidth on that. All right, so we
killed to have any better internet at my house.
Oh,
I
really?
think I get 10 download. I'm in Hawkinson area.
Oh, wow.
So we're pretty terrible out here. We have literally one DSL line that supplies the whole freaking area.
Oh, man, yeah. Yeah, that's rough.
Yeah, you can't even watch a movie and be on the internet at the same time. It's worse than dial-ups.
Wow. Yeah, brutal. Yeah, I've been lucky, and I used to have to do all my uploads at Clark, because like my videos and stuff, because it's usually like a gigabyte or two, and Comcast seems to have gotten pretty good, or Xfinity, whatever they call themselves, seems to be pretty good now. I'm getting like good upload speeds, so.
Oh yeah, my parents in the city, they can get upwards of a gig.
Oh wow, cool. Unlimited 5G hotspot. Oh, that's pretty cool. So we can you know, see connections between machines that are directly connected or indirectly connected. We might be interested in other things. For example, is there redundancy? Suppose that this machine and this machine want to talk to each other. Well, we know they can do it. They can go through these machines and hop down. But is there redundancy? If one of these machines goes down, is this connection severed? And the way I've drawn this right now, the answer is yes. You know, if this machine goes down, there's no way for this machine to talk to this one. Or if this link breaks, if someone runs over this with a lawnmower, the connection is gone. But, you know, if I had something like this, I would have 2 possible pathways from here to here. One would be, you know, this old link, but I could also come down here and come up here and go across. And now if this link gets chopped up by someone's mower, right, I still have connectivity. And so we can analyze, we can describe a lot of situations by thinking about them as graphs, and then we can ask questions about the situation in terms of properties of these graphs. So anytime that we have redundancy, we're going to find we have loops, right? The fact that I can get from here to here through 2 different paths is related to the fact that I can get from here back to myself. And sometimes loops are good, sometimes loops cause us problems. We can also ask, is there a critical node? And this node right here looks pretty critical because everything over here and everything over here, their only connection is through this one spot. So that might be a critical failure point. And I might have, a million nodes back here, and I might have a million nodes over here, and they're all going through this one point. And that poor machine's going to get overloaded, and it's going to overheat, and if it fails, everything's going to get disconnected. So we use graphs to study a lot of different situations. Another good example of a graph is just sort of a map. If you made a map of intersections in a city, you could see how you get from one point to another. And in that case, we might have one-way roads. Some of these arrows, some of these lines might actually look like arrows. And in this kind of graph, which we call a directed graph, we might, discover something like this. And one thing that's interesting here is if I'm at this point A and I want to get to point B, it's very easy. I just go down this one road. But if I'm at point B and I want to get back to point A, I have to come from here, over to 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 here. It's a very expensive trip. I'm thinking Portland, I'll admit it, right? Where you miss a road and now you're in like this jumble of one-way roads and you have to go over to like Salem or something to get to where you're going. I just don't know Portland. So, we can sort of see relative difficulty of paths from one point to another. And we can also have what's called a weighted graph. Now I've drawn, these arrows approximately the same, but we could number these to represent distance or represent time, or if this was an interstate, to represent the cost of the tolls on a road. And so this might be, 2 and 4 and 3 and 1 and 2 and 1, 1, 3 and 2. And maybe there's a way to get from B back to A, and maybe that's a really expensive road. And now if we were at B and we said, what's the fastest way to get to A? Well, we could take one road and get there, but maybe for some reason there's construction on that road that takes a really long time. Whereas if we take this less direct route, we go over here and here and here and here and here. It only ends up taking, 1, 2, 3, 6, 8, right? And that turns out to be faster or cheaper or whatever. So we want to formalize some of these ideas of looking at, points connected with lines, possibly having directions on these, possibly having numbers associated with like weights or times or costs or something like that. And these are all concepts in graph theory. Things to be keeping in mind, right? Again, the placement of these on the paper is not important. The way I draw the lines is not important. This graph is exactly the same as if I had drawn, some kind of graph that looks like this. What's important is, from here to here, there's a connection that goes in this direction and has a cost of 1. And, sometimes we might have negative costs associated with these. You might, get back some time in some non-physically possible way, or you might get, paid to drive on a road or something, right? And these can have negative weights associated with them. And now all of our algorithms for calculating, the cheapest way to go from one point to another, all of those change. A lot of them break. All right, I gotta do something about the sun. figure it out. I'll avoid that spot. There we go. All right, so let's oh no, destroy the sun. Let's see, is this going to get into scene graphs with parent node and child node relationships? So when we start talking about parents and children, then we're talking about trees. And sometimes we talk about trees in this course. I don't think we're going to get to it. So we'll leave trees for CSE222. But trees will be an example of a type of graph where we have this sort of, you know, directionality from each node to another and so on. All right, so let's do this a little bit formally. So a graph G, we're going to write it as a tuple, so an ordered pair of two sets V and E. And V is a set we call the vertices. And this is a non-empty set, so we have to have at least one vertice, one vertex. And E is a set that we call the edges of the graph. And E could be empty if we want. It's a really kind of silly graph in that case, but that's okay. And each edge has one or two what we call endpoints, which are vertices. And the edge, we'll say, connects its endpoints. So for example, here might be our vertices, and let me call these A, B, C, D. So there's our set of vertices, and our set of edges might be, you know, I don't know, let me call it little a, little b, little c, little d, little e. And our graph is this pair of vertices and edges. And each edge, A for example, connects its endpoints. So A's endpoints are big A and big B. And we could have an edge that, you know, we could have an edge F here that connects D to itself. Right, so that's the sense in which an edge can have a single endpoint. So it could be, you know, a loop that connects a point to itself. That's still considered an edge. And we could have vertices that aren't connected to anything. We could have something like this. Where we have G and H connected together, but they're not connected to anything else in the graph. And we've got F that's just sitting off by itself and has no edges connecting it to anything, and then we've got this other graph here. And we could have, you know, a second edge J that connects G and H together. And we could have another edge K that connects G and H together. So just to be a graph, not a whole lot of restrictions. We're not going to worry too much about this case here. So we're going to mostly deal with simple graphs. And a simple graph means we have at most one edge connecting a pair of points. So if we throw this away and we just stuck with something like, you know, G and H and had an edge I connecting them, now we're back to a simple graph. And that's most of what we'll deal with. All right, so examples, think of computer networks, you know, maps. maps, cities being connected by highways, intersections being connected by streets in downtown, things like that. Alright, so a directed graph each edge is given by an ordered pair of vertices for example u comma v, and we would think of this as u and v. If those are vertices, we would think of this edge as going from u to v. All right, another example of graphs would be an acquaintance graph, right? So we could make a graph of people who know one another. So, you know, we have people called A and B and C and D. Right? So there's a fairly random graph of people who know each other. And so, for example, person C knows a lot of people. They know persons D, E, F, and G. And person D knows person H, but also person J. And so person H knows person C through person D. Person H also knows person C through I, who knows B, who knows C. So yeah, we're at the Oracle of Bacon, right? So this is how you talk about things like degrees of separation between people. And you know, I and G may never have met, but I knows B, B knows C, C knows G. So you only have to go through 3 people for person I to get an introduction to person G. All right? This is what, you know, Facebook and Google and all of these engines do all day long. When you know, go onto LinkedIn and it says, you know, you've got 2 levels of connection to so and so, right? This is what's going on. There's graphs of all of these connections between people, and from these graphs, from knowing who C's friends are, right, you can tell how closely linked C is to somebody else. And you can find a network of connections that will get you from one person to another. And then you can do all the kind of evil things that you know, people do with this data and all that kind of stuff. Yeah, this is a really nice example of recursion. A nice application area for recursion because, well, we'll talk about that in 222. But you know, if I want to know who D is related to, all I have to do is know who H is related to, and who J is related to, and who C is related to. And that's the collection of people that D is related to. And how do I find out who J is related to? Well, I just find out who A is related to, and so on. It's also really good for blowing up stacks. All right, so this is you know, an example, and you know, if you do this and you find something like this, right, you can do click detection. So here's 3 people who know each other, but there's no connection between any of these people and any of those people. So it's like, you know, a separate group. And that's interesting if your business is you know, marketing data on people, and you're doing really good sales over here and not very good sales over here. Well, all you got to do is find a connection between one of these and one of those, and if you can figure out what that is and exploit it, you potentially can expand your market to a large number of additional customers. right? And you look for trends like that, and you start to change your advertising to try to bridge these gaps, and so on and so forth. And this is what a lot of companies do for a living. So that's another example of graphs, acquaintance graphs, things like that. And the overlying theme in all of this is that, you know, we can take a problem or, you know, a situation we want to analyze. We can think of it in terms of a graph, and then if we can analyze this graph using computers, we end up analyzing the situation that the graph describes. So we want to think about how to take graphs and represent them in a computer. And so to do that, we're going to need some more definitions and some more terminology. And so here's a definition. Two vertices, U and V, are adjacent if they're connected by an edge. So edges connect vertices. If two vertices are connected by an edge, we say those two vertices are adjacent, or sometimes adjacent to each other. And if we call this edge E, then we could say E connects U and V. And we could also say E is incident with U and with V. Alright, so we're just doing some definitions right now. And this will just formalize and standardize our language for talking about all this stuff. So N of V is what we call the neighborhood of vertex V. And it equals the set of all vertices connected to V. I don't have any good graph pictures left. Oh, there we go. So the neighborhood of B would consist of A, C, and I, because those are all the edges that are connected to B, directly connected. The neighborhood of C would consist of B, D, E, F, and G. Alright, so the neighborhood of V, which we write as N parentheses V, is the set of all vertices that are neighbors of V connected to it. Alright, the degree of a vertex V, and we sometimes write this as degree parentheses V, equals the number of edges incident to that vertex V. So let me make a more proper graph that we can play with. Here's a reasonable looking graph. Alright, So the degree of A would be what? It's the number of edges incident to vertex A. So how many edges are incident to A? And remember, a vertex is incident if it connects that vertex to the other vertex. So yeah, 2. So the degree of A is 2 because we have an edge here and an edge here. The degree of B is what? Four. Anybody else? Degree of C? A million SpongeBob doubloons for the degree of C. Not really. 3. Awesome. Right? 1, 2, 3. So we're just counting. Degree of D is going to be 1, 2, 3. And the degree of E is going to be 1, 2. We're just counting the number of edges that are connected to, the number of vertices that are connected to the vertex in question. I am so denied. Alright, we'll live with it. Alright, so that's the degree of a vertex. So there's a cool little theorem we can spin out at this point. This is our first graph theory theorem. And by the way, let me make a footnote on here. When we talk about degree as the number of edges incident to a vertex, I'm going to say loops count twice. So if I have a vertex like this, I would say that I have 2 edges incident to this vertex, even though it's one edge, but since it's a loop, right, it's an edge beginning here and there's an edge ending here, I would actually count that twice. And that kind of peculiar counting is important for this following theorem. So here's a cool little graph theory theorem. 2 times the number of edges equals the sum over all vertices in V of the degree of the vertex. And we're talking about undirected graphs here, so there's no arrows on these edges. So 2 times the number of edges should be the same as the sum of the degree of each vertex. Well, let's check that out here. The sum of the degrees of these vertices, 2 plus 4 is 6, 9, 12, 14. And how many edges do we have in our graph? 1, 2, 3, 4, 5, 6, 7. So for this graph, it certainly works. 2 times the number of edges was the same as what we got when we added up the degrees of each vertex. And it's a good theorem, it always works. Why do you think this works? Why is it that if I add another edge, my total degrees, if I add them all up, is going to go up by exactly 2?
Because for every edge, there's 2 vertexes.
Yeah, for every edge, there's 2 vertexes. If I wanted to add an 8th edge, it's got to begin at some vertex. It's got to end at some vertex. And whichever one it began on, that degree is going to go up by 1. And whatever vertex it ends on, that degree is going to go up by 1. And so my sum is going to go up by 1 plus 1. and my number of edges went up by 1, and this relationship will still hold. And so if I know that this works for a graph with 7 edges, I can kind of prove that it's going to work for a graph with 8 edges by just this kind of argument. Now you got to do some hand waving and say, without loss of generality, suppose I start here and end there and so on. But if I know that, a graph with 8 edges will have degrees adding up to 16, can I show that if I have a 9th edge, I'll end up with a total of 18 for my sum of degrees? Yeah, because, add one more edge, it's got to begin somewhere. And it's got to end somewhere else. Even if it ends with itself, that's going to raise the degree by 2. Right?
Can I ask a more generalized computer science question here?
Yeah.
So, I've read that a common design in computer science is a thing called a scene graph, where there's like a root node and it has children all connected, and we could connect this to this, where the root node's going to have the highest number of degrees, and all the children are going to have smaller degrees, and they're all connected to the root node. Would there be any different name for that kind of a graph, where there's just one node that every other node is connected to, instead of here where, C is connected to B, and A is connected to B, and there isn't like a central node?
There probably is. I don't know if I know it, but a version of what you're describing would be what we'd end up calling a tree. Except that with a tree, you don't necessarily have a direct connection from every node to the root. But in a tree, we typically have something like this. Kind of like what we were looking at when we drew out the recursion of Fibonacci calculations, right? And so in that kind of structure, this is called the root. And there's a path from the root to every node in this graph or this tree. And there's other properties. There's typically no loops and so on and so forth. But a scene graph, I think, is something slightly different from a tree. I think it's more general. But I don't know if there's a particular name for that. And someone asked, why is the computer science world so obsessed with the number 2? It's a really good question, because we got 10 fingers, not 2. And you wonder if, you were on a world where everybody had 3 fingers, would everything be base 3 instead of base 2? And it's intriguing to me that, the English system of measurements, for example, you have a gallon and a quarter of a gallon is a quart. And if you break that into half, you get a pint. And if you break that into half, you get a cup. And a cup is 8 ounces. And there's all these powers of 2 in these measures of calculation that are, hundreds of years old. And the metric system, which is supposed to be the modern way the scientific world works, is all base 10, which is, human digit centric. So we scale up by a factor of 10 from one unit to the next. And that always felt kind of backwards to me somehow. Like, it seems like the scientific one should be more binary in nature. But that's just my editorial. All right, so just to close the loop on this, no pun intended, if we look at this theorem and we know that it's true for n, we can prove that it's true for n plus 1 by using this argument that, this n plus first edge has to start and end somewhere. How would we formalize that into a proof that this is true for any number of edges? What would be the technique we'd use? Or what kind of proof?
Well, I mean, it's mathematical induction.
That's mathematical induction. We could induct on the number of edges. And now you just have to show that there's a base case. And maybe our base case would be, to start off with a single edge. And if we only have one edge, we've got either, this kind of situation, or we've got that kind of situation. And so this is degree 1 and 1, this is degree 2, and our formula holds for one edge. Or, you know, you could even start your base case with 0 edges, because you don't need to have edges in a graph. And if you have 0 edges, the degree of every node is 0. And so 2 times the sum of the degrees is 0, number of edges is 0, 2 times 0 is 0. So yeah, we could use induction to prove this theorem. We're not going to do that, but we kind of already did. Oh man, I'm like so close.
You need to take one of those books off your pretty bookshelf in the background.
I could, man.
Costco has some pretty cheap blackout curtains.
Yeah, if I had any curtain, I think it would work. Alright, that'll work. So I've got this pile of books on top of paper underneath a box, but that works. Alright, so there's one theorem related to degrees. Up here. All right. So given this theorem, we can now state another theorem. This is kind of like a corollary. It's sort of like a mini theorem that follows from this first one. So let me call this a corollary. And this is for an undirected graph. We're not putting arrows on here yet. We're still talking about just undirected graphs. So corollary, a graph always has an even number of vertices with odd degree. If I count up the number of vertices in a graph with odd degree, I always get an even number. I could have 0, 2, 4, 6, 8, 10, 12, but I can't have 5 vertices with an odd degree, for example. It's always got to be an even number. And so our sample graph, right, we had 1, 2 degrees, 2 vertices with an odd degree. Before we made that change, we had vertex C and D, both had degree 3. We had 2 vertices with an odd degree. And it's really a consequence of this theorem that this fact also follows. So why would that be? Why can't we have an odd number of vertices with an odd degree? Any idea?
Well, that's when you're, as soon as you multiply by 2, you kind of have the number becomes even. So if you have odd vertices, you have to at least still get even edges.
What does undirected graph mean? What's the distinction there again?
We're not putting arrowheads on our edges yet.
Oh, okay.
So we're going to expand this in a minute to directed. So we still do have some vertices with odd degree. B and C, for example, have degrees 3 and 5. So those are odd numbers. But why do we have to have an even number of those?
Well, for every connection, it is linked to another connection in a different node. So for them, there can't be a connection that isn't accounted for in another node. So,
Right.
it took me then to bring this into some better form of English, but the idea that like you can't, connections comes in kind of groups of 2s.
Mm-hmm.
There will never just be like just one connection. So
Right.
for the reason why there has to be an even number of odd vertices is the fact that my brain has it, but I can't.
Right. Let's think about evens and odds, right? We've done some work with those, and one way we've done work with those is by thinking about things modulo 2. If we work modulo 2, an even number is always congruent to 0, an odd number is congruent to 1. And this is one way to see, if you take an odd number plus an odd number, that's going to be congruent to 1 plus 1, which is 0, which is going to be an even. If you had an odd number of odds, so let's say, you have n evens and m odds. Well, if you add up the degrees of these, right, you're going to get something congruent to n times 0 plus m times 1. N times 0 is just 0, m times 1 is m. And so the sum of the degrees of all vertices will be congruent to just the number of odd vertices that you have, modulo 2. If the number of vertices with odd degree is itself odd, this will be congruent to 1. But 2 times the number of edges is going to be congruent to 0. So it's going to be congruent to 0 times the number of edges, which is just 0. And so if m was odd, 0 would be congruent to 1, which is not the case, modulo 2. So this number m has got to be congruent to 0, which is just another way of saying m is an even number, and so the number of vertices with odd degree is even. And this is just a long-winded, modular arithmetic way of basically saying, like, if you add a bunch of numbers together and you want the result to be even, which it has to be because it's got to add up to 2 times something, right? Your odd numbers have to kind of pair off. So those will pair off together, my result will be even. But if I have an extra, odd number kicking around somewhere, my sum's going to end up being odd. So pairs of odds will cancel, and evens will, just leave me with an even. But if I'm going to have an extra third odd number here, I got to have, some other odd number somewhere to cancel that and make the sum even. Alright, and someone said, what about the case where there's one vertex and a looped edge? Well, if you have one vertex with a looped edge, the degree of this vertex is 2 because we count loops twice. And the number of edges is 1, and so twice the number of edges is the sum of the degrees, and there's no vertices with an odd degree, so the number of vertices with an odd degree is 0, and 0 is an even number, because it's 2 times an integer, 2 times 0. So this works even in that case. All right, so this gets a little more interesting with directed graphs. And so in a directed graph, we basically put arrowheads on our edges, but we can formalize that a little bit. So directed graphs. So if we think of this ordered pair u comma v, we can visually think of that as an arrow on the edge going from u to v. And so more terminology, we can say u is adjacent to v. We can also say v is adjacent from u. Our English teachers may not like that. That's okay. We also say u is the initial vertex And we can say V is the terminal vertex. And now we're going to define two versions of degree for a vertex. We're going to define the in degree of a vertex. So a vertex, let me just call it V. And we'll write this as degree with a minus sign on top. And this is the number of edges basically going into V. So the number of edges adjacent to V, but it's basically the number of arrows going into that vertex. And the out degree we'll write as a degree with a plus sign of V. That's the number of edges leaving V. Alright, so examples are easier than words sometimes. So let's make a graph. And let's put some arrows in here. Boom. 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 And I said we're going to stick with simple graphs where we only have one edge between a pair of vertices. This is still simple. I have one edge going in this direction, one edge going in this direction. If I had two edges going from B to C, then it would no longer be a simple graph. Alright, so there's a sort of randomly chosen directed graph. So let's look at the in degree of each vertex. In degree is the number of edges going into a vertex. So for node A, vertex A, how many edges are going into A? Yep, just one. How about B? Two, good. I think you got it. We'll do one more. How about C? Yep. So again, we're just counting, right? D, we have one edge going in here, and that's it. So that's just one. E, we have one edge going in here, and F looks like we have two edges going in. And then out degree is the same thing, but we look at the number of edges leaving a vertex. Alright, so how many vertices leaving A? Alright, also two. B looks like we've got one edge coming out of B. C looks like we've got two edges coming out. D, we've got 1, 2, 3 edges coming out. E, there's a single edge leaving, and F, there are no edges leaving. So same process, just different calculation. And we have a similar theorem to what we had for undirected graphs. Let's add up the total in degree of all of our vertices. 1 plus 2 is 3, 5, 6, 7, that adds up to 9. And if we add up all of the out degrees, 2, 3, 5, 6, 7, 8, that's also 9. And if we count the number of edges, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so there's a similar theorem which says if you add up the in degree of all edges, you get the same thing as if you add up the out degree of all the edges, which is exactly the number of edges in the graph. And if we decided to look at this as an undirected graph, right, this would just be, you know, the degree of each vertex. This would be the degree of each vertex, and so when you add them up, you get twice the number of edges. So that first theorem is kind of a special case of this theorem. All right, so sample graphs. We've been drawing random graphs just to have something interesting to work with, but there's a series of particular graphs that we'll talk about somewhat. So the first is a complete graph. And a complete graph, Kn, is a graph of n vertices. And a complete graph, basically, you put an edge between every pair of vertices. So K2 just looks like this. K3, we have 3 vertices and we have an edge between every pair. K4, we have 4 vertices and we have an edge between every pair. K5, we'd have 5 vertices. And we have an edge between every pair. So this is kind of like the most edge-dense version of a graph. So a complete graph is a graph that has no edges left out, actually. So a complete graph K5, for example, we have 5 points, 5 edges, 5 vertices, but every possible edge we can draw, we draw. So we don't skip any edges. Alright, we'll also talk about cycles. So cycle Cn will be, it'll look like this. So C2 looks like this. C3 looks like this. C4...
Seems like for all even ones, it will always divide into triangles, but if for all odd ones greater than 3, it would contain the same shape inside of it.
Oh, interesting.
Like, the pentagon contains a pentagon in the middle, but the rest are triangles.
Is this Corbin's complete graph theory? That's cool.
Maybe.
I haven't thought about that. Yeah, sketch out some bigger ones, see if that holds. That's intriguing. So a cycle, right, C5, you draw 5 vertices, and you simply connect one to the second to the third to the fourth, fourth to the fifth, and fifth back to the first. So it looks like that. And you know, it's a subset of the edges that we had here, but it's basically kind of like the smallest graph that we might have that leaves everything connected to something. So those are called cycles. And then the other one we'll talk about sometimes is a wheel. And a wheel Wn is just a cycle Wn, but with a center to it. So it's like a spoked wheel. So W3 would look like this. But we throw an extra point in the middle and connect that to each vertex. W4 looks like cycle 4. So we've got that, but we throw an extra vertex in the middle and connect it to all the other vertices. So it's like a wheel. So those are some sample graphs that we'll refer to throughout what we're talking about. And then another definition on here would be a subgraph. So remember, we can think of our graph as you know, vertices and edges, this ordered tuple. So if I have a second graph, WF, I can say this is a subgraph of VE. If my set of vertices is a subset, and my set of edges is also a subset. So I said a minute ago that this was like a subgraph of that, right? Basically, I have the same vertices, and I can just remove these internal edges, and K5 turns into C5. C4 is also a subgraph of K5 because, you know, I could pick out these edges, and these vertices and these edges, and that's the same graph as that. In fact, I think that any simple graph with 5 vertices is going to be a subgraph of K5, because this contains every possible edge from one vertex to another. So formally, we think of a subgraph as just saying the set of vertices and edges are subsets of the other graph's vertices and edges. And then we can change graphs from one to another. So what are the things we can do to change a graph? We can remove an edge. So if we have a graph and we take off an edge, that's really just our original set of vertices, and the set of edges take away the singleton set containing that edge. Sorry, that's a tuple. So if I want to remove this edge from the graph, we just remove that edge. Right? It doesn't affect the number of vertices, it doesn't affect anything about the vertices. It just takes that edge out of the set of edges. But a more interesting modification is contracting an edge. And here we remove an edge, but then we connect, or we join its vertices together. So after we remove this edge from this edge, we basically treat D and E as being the same vertex. And so, you know, I might take this out of here, and this would come down right here. And that would be contracting this edge that had connected D and E. And we can also remove a vertex. And to remove a vertex, remove all incident edges. So if I wanted to remove vertex B, I would take B out of my set of vertices, and then I would take these edges out of my set of edges. So kind of the canonical thing you might imagine doing if you were asked to remove an edge or a vertex. All right, so that's some examples of graph. It's some terminology, it's some basic theorems, it's some operations we can perform, it's some concepts about subgraphs and so on and so forth. Why do we care about any of this, right? Well, we've said, you know, we can represent lots of situations, lots of arrangements of things by making a graph corresponding to them. And one of the challenges with graphs is, you know, when we draw them on paper, we all have our own sort of way that we might draw graphs. This might be our graph ABCD, right? But I could draw exactly the same graph like this. And that's the same graph. It's the same set of edges, the same set of vertices, the same connectivity between vertices. A and B are connected together. A is connected to B and D. B is connected to A and C. C is connected to B and D. D is connected to A and C. It's exactly the same graph, but to us, these look very different, right? And we need to know that if we take these two things and we flip them over, right, then we've got the same original graph. And the names of these vertices are not necessarily relevant. So, you know, I could simply have a graph that looks like this, and it would be the same graph as this. And it would be the same graph as this. Or this. And so drawing these on paper is sometimes useful when we're brainstorming and trying to come up with ideas, right? But when we're working with a computer and we want to describe a graph to a computer and then have a computer do some analysis on it, find distances from vertex to vertex, look for cycles, things like that, we need a way to take this information and put it into a computer, and we do not want to do it visually. We don't want to just, you know, take a picture of a drawing and have our system try to work on that. So we want to think about representing graphs inside a computer. Erpresenting. And so that's what we're gonna start with on Wednesday, is ways to represent this, and we'll see a few different ways to do this, mostly using arrays, right? Using matrices, or maybe using linked lists, which we'll talk about in 222. But CSE215. But there's ways to represent this information in a computer, and depending on how we represent it, we can write code to do various analysis and modifications to these things. So we'll play around with that a little bit on Wednesday, and then we'll talk about the question of, you know, how do we know that this graph and this graph are the same? What does it mean to say that they're the same? I mean, to us, we see that we could move these points like that and turn this into that. But what does this mean sort of more rigorously, and how would a computer make that determination? And then we're going to start talking about paths. And paths are the whole question of how do you get from one vertex to another. If I'm sitting at vertex A, I could go from here to here to here to get to F. I could go from A to C to F. I could go from A to B to C to F. I could even go from A to B to C to B to C to B to C to F. Or from A to D to E to A to D to C to B to C to F. So we're going to look at paths, different types of paths. We're going to ask questions about paths leading up to what's the shortest path from one point to another. But also questions of, you know, is there a way to get from one vertex to another that visits every vertex along the way? Is there a way to get from one vertex to another that travels along every edge along the way? So these will be particular types of graphs called Euler graphs, Hamilton graphs, and so we're gonna work with a bunch of these different concepts, but mostly related to graphs. So that's our main plan for the rest of this unit, is talk about representing these graphs inside computers, look at isomorphisms, and then delve into paths. And we'll end with something called Dijkstra's algorithm, which is a way to find the shortest path between two vertices in a graph. And Dijkstra's algorithm is one of these things that you'll encounter again and again in computer science. You'll certainly encounter it in projects at a university. You might encounter it in projects in 223. So this will be good stuff. So we'll plan on doing graph theory Friday and Monday, and hopefully finish it up on Monday, and then Wednesday, it'll be a short week next week. Wednesday we might start in on the final unit of the course, which is natural language processing and grammars and things like that. So lots of good stuff coming up. All right, send me an attendance ping, please, on the way out, and I will see you next time. Have a great afternoon.